Okay, so the last thing I want to talk about is human exposure and exposure in general to radiation. And I'm pretty much just going to show you some slides and talk a little bit about this, but I'll give you some references because if you look at these alpha, beta, neutron, gamma radiation that can be produced by nuclear reactions, you can see that some of them have the ability to penetrate through human skin and through concrete. So you can see gamma radiation, which is electromagnetic radiation, can go through lots of things. It's got a really high frequency, and so a short wavelength, and so it doesn't interact with much stuff. And so different things protect you from radiation. Wearing clothes would stop you from alpha particles, hitting your skin. But there's different effects that can happen from any of these. They can ionize. They talk about ionizing radiation and non-ionizing. So if you look at what are some of the sources of radiation that you're exposed to, you can look like way down here, the doses that you have, and these are in REM. REM is a way of looking at these Rankine equivalent man. That's what that stands for, in millirem. And so there's different, we've talked about decay rates, but then there are rads and REM and these different units that talk about how they're deposited and how they interact with tissue. And so REM actually has a factor that's multiplied by how dangerous it is. And so you could look up exposure, but RAD and REM are two of the common ones that you see. And so I'm going to show you just in the concept of REM how these just imagine it's this unit that, and I'll show you what it means. But even going up in a flight, you get more radiation exposure. Even drinking your normal drinking water has some radiation in it, and that's just sort of an understanding that you have to have. Safe drinking water, there are limits to anything, and there's always contamination in our water. There's no such thing as pure water. It would be too expensive. So we live with a limit of what our exposure is. And we're typically okay with that if we don't think about it too much, so it seems. If you go in for a chest x-ray, you get 10 millirem. The normal cosmic radiation gives you exposure, and so there's not much you can do about that. Your own body emits, not much you can do about that either. But we typically get a public dose of about 100 millirem a year. And if you go back, just from background, you can see the background dosage and then the annual dosage for Americans. And then if you go get a whole body scan, there's a lot of exposure. And then if you work at a nuclear facility, you get even more. And you always think to yourself, well, why, you could find out what's wrong in a person by giving them a CT scan every year, but you're getting a huge dosage of radiation, which can cause damage too. So even though you're finding things, you might be causing other damage by getting a CT scan. So that's just a general understanding. So what happens when you start getting into these REM exposures? So remember, that previous slide had millirem. This is actual REM exposure. So if you worked at a nuclear plant and you got 5,000 millirem, that's 5 rem, and you do start to see changes in your blood chemistry, so changes in what's going on. We can detect that something is happening. And then if you get 50 rem, you start to get sick. That's sort of like lightheadedness and nausea is a good indication that you're overexposed to anything. But you can see as these REM exposures, high dosage of radiation, you get vomit, you start losing your hair, you start hemorrhaging, you can die if you get a 400 REM dosage. You start to destroy things in your body, damage to your system if you have 2000, and then you can obviously die as a result of overexposure and radiation. Some of it's just tissue damage. Others are, you can see direct radiation where it hits a nuclei and changes an atom, and that can have DNA modification issues. You can have radiation hit other molecules, and then they can create molecules that can ultimately go and damage DNA. So it's direct and indirect radiation. I found this interesting document. It's declassified from World War II that Oppenheimer, who was a early physicist chemist. So I've linked this in here. I think it's worth reading. It sort of talks about like how far from a nuclear test can you be where you're getting radiation exposure, and all this was sort of real stuff that was going on. And we started harnessing this. If you think of like the Manhattan Project in World War II, we started looking to radiation where we started making this take place, this fission occur on Earth here. And you can see that in 1942, the first fission reactor was created with the uranium-235. And to get uranium-235, we built this huge reaction chamber, as part of this project. And you can see this was in Oak Ridge, Tennessee. It was this huge diffusion chamber where we took uranium and we sent it through because we needed to get one isotope that was fissionable. And it took this huge facility in order to generate this. And I just think this is kind of a neat picture showing how the uranium was isolated to make weapons and nuclear power. So you need a critical mass in order for fission to occur. So we started talking about the energy and exposure, and the reason I'm moving to this is because when a nuclear facility or bomb goes off, there are nuclei that emit radiation, and we have to be concerned about something like that. Even a nuclear power plant could have a leak and emit this, and so one of the reasons this happens is because you have this fissionable material, and you can have a subcritical mass, which means you don't have enough for all these productive reactions and energy to be produced. And when these happen, you split nuclei, you get off energy as well. Because mass goes missing, and that missing mass turns into energy. And when you have a critical mass, you get even a bigger explosion. And so think about, if you were creating a weapon where you had to have a critical mass of uranium, that's pretty dangerous because, in a sense, you have to make that critical mass come together. So you have subcritical masses, and then you have to put them together so that a big explosion takes place. And if you look, your book has designs for these first couple nuclear bombs that were dropped in 1945 on Hiroshima and Nagasaki. And you can see that the way these were connected, this one was a uranium-235 bomb, and they had two different pieces that were subcritical, and then they, at a certain height above the ground, these two particles, this detonator went off and combined these two critical masses, and then a big nuclear explosion, fission nuclear explosion occurred. And then there were other models where, like in this Fat Man bomb, plutonium middle, and then they had these explosions that pushed the plutonium in this case down into the middle to make a critical mass occur. And you can see that these were horribly destructive, and the radiation, the particles that were emitted over this area are still there and emitting, and that would affect cancer rates and health in these areas where these bombs have gone off. I put this is an interesting video. That all this happens because of energy, and this is Oppenheimer here and Albert Einstein. You can tell because of his mustache and hair. I think that's a kind of a neat picture. These were both kind of amazing minds that were working on this problem. And there is an interesting video. This was a NOVA video, and I found an old segment of it, and it's very poor quality, but it shows Oppenheimer's response to this nuclear weapon that he had a hand in creating. And so, anyways, I think that's worth looking at. So the first fusion bomb after fission, so uranium plutonium bombs where you just need a critical mass together, was built in 1952. The first set off was done, and these take really high temperatures. So you use a normal fission bomb to get to the high temperatures, and that's a core reaction. And then they bombard this lithium deuteriide, and it produces hydrogen 3, and you can get a nuclear bomb. But I give you an example here of the basic process that takes place. If you look, you can there's links I put out here if you want to learn more about it. But basically, two smaller nuclei come together and make a bigger nuclei, and that's the concept of fusion. But it only happens at really high temperatures, and the only way to get to high temperatures is to set off a fission bomb. So, but you can use this to do things other than just make weapons. You can generate power this way. And so if you have a core of radioactive material that is producing energy, you can use it to create steam and ultimately turn a turbine to generate electricity. And you obviously have to worry about this core breaking down and leaking out. You don't want that. And so oftentimes they have these control rods up here that help absorb neutrons to control the fission that's taking place. So you can slow the fission down if this core gets too warm. And that's basically what's going on with this. So anyways, I just thought it's sort of a neat thing to talk about when you have time. And if you have time and you want to look over this type of stuff, I put some interesting links in here. I just think it's kind of a fascinating field of chemistry that's so different from the chemistry that you learn in the previous section. So